Hello students, so welcome to the course of wave optics, and today we have lecture number 13 and we are going to continue the concept of coherence that we have started in our last class. So today we have lecture number 13. So in the last class we started the concept of coherence, and the concept was something like that. In a system, suppose is a system where the atoms are distributed randomly and they radiate in a random manner like this, then the corresponding radiation can be given. Suppose they are emitting and the emission can be given, represented by this discrete waves, where up to certain time we have pure harmonic radiation and after that there is no phase relationship, and this particular length at which, this particular time length at which we have a pure harmonic wave, we call the coherent length. And we also mentioned in the last class that this coherence, this phase relationship depends on that how monochromatic the light is. For a finite harmonic wave, we have a function that has a finite width. That calculation we do. So let us go back to this concept that this time length at which this wave is emitting having a phase relationship. After that there is a sudden phase jump. You can see this dotted line shows that these is the locations. These are the locations where there is a sudden phase jump. We don't have any phase relationship after that. So only for this length, this time length, we have the phase relationship of the wave, and this tau 0, the time length for which we have the phase relationship, for the time window for which we have the phase relationship, we call this as coherence time. Coherence time. Now from this coherence time we can have something called coherence length. This coherence length L, I put a suffix C here to make it coherence. This C stands for coherence. This coherence length can be defined as tau 0 multiplied by C. C is the velocity of the light in medium in a vacuum, and then if I multiply it with this coherence time, the length during which the light travels, within which time period t0, the length is called the coherence length. Now this is C divided by delta nu, because we know that tau 0 is related to 1 divided by delta nu. Here this delta nu, this can be related with with something called delta lambda. Delta lambda is the wavelength distribution that the source have, and this is called this thing called line width. This is called line width. So nu, we know that it is c divided by lambda, and from that we can find out delta nu to be, if I make a derivative both sides, so we should get minus of c divided by lambda square delta lambda. If I put the mod sign, this minus sign will no longer be there. So this quantity, I can, with this relation, I can correlate delta nu with the line width delta lambda, and then my coherence length LC will be c divided by delta nu. So c divided by c delta lambda multiplied by lambda square, neglecting the negative sign, taking the mod sign. So it should be simply lambda square divided by delta lambda. So the line width delta lambda is simply lambda square divided by the coherence length. So if the coherence length is known, then I can calculate what is the delta lambda, that is the line width. If the line width is known, I can calculate what is the coherence length. Now if the delta lambda, that is line width, is small, then from this expression it is clear that the coherence length will also be very high. So for a very monochromatic kind of light where delta lambda is small, then we can expect the coherence length to be very high. On the other hand, if we have a source with a very large lambda span, then the coherency is also less, that means coherence length will also be very less. Well, after having this qualitative idea, now in the next step we will going to discuss in detail what is the meaning of superposition of two waves, and based on the concept of superposition of two waves, how one can calculate the coherency. The degree of coherency can be calculated, and that calculation we will do here in today's class. So normally it is very difficult to have a purely coherent source or a partial or a purely incoherent source. However, all the sources are partially coherent. So what is the meaning of partial coherence? That we will going to discuss now. So let us write, this is concept of partial coherence. Okay, so let us have a source here, say S, emitting light via 2 point. This is one source, and then it is emitting the light via 2 point S1 and S2, and these two light is merging at some point, they are superimposed at some point P. So the first light going through S2, S1 to P, I call it as path 1, and another is path 2. Now we define two fields, say ES, that is the field at source point, field at the source point, S. Similarly, this is the first definition. Second definition is E1S and E2S are the field that is the coming from S1 and S2 are the fields that superposes that are superposed at point P. So obviously, third point, E1S and E2S maintain some polarization, that of the same polarization that of ES. So they have the same polarization that of the source field ES. So since all the waves are having the same polarization, all the fields, so we can consider, so this is the condition, we can have all this function as scalar function. Because we consider the polarization to be same for everybody, so we can consider this as a scalar function. Now the field at ES, the field S ES is a time dependent field. I drop the vector sign because I considered that everything is a scalar function to make life easy. Then I can write it as half of some field E plus the complex conjugate of that one. So that means this is the field that we defined, this is the real part of some field E which is time varying. Now I define what is my E. So ET, that is a time dependent field, is E naught e to the power of minus I omega t e to the power of I phi t. So that means I have the explicit form of electric field which is a time function, and we define it in this way, and a phase is there, a time dependent phase is there. This is accounts for the departure from the monochromicity of the source field. That means how the source field is departed from the monochromaticity, then that will be defined by this phase. If phase is 0, then it is highly monochromatic. If we have some value, then it is differ from this monochromaticity. So this is a time dependent phase. Okay. Now, after defining all these things, I need to define the fields at this E1s and E2s that I want to define. So, that before that I say that this E, the field that is coming here, the field that is reaching here from here to here and here to here, I define these two fields as E1p, that is reaching at the point P, as half of, say, some field E1 and E1 star, that is real part of some field E1. I'm going to define what is E1, but let me first define the fields that is there due to path 1 and path 2 at the point P. This is at the point P. Similarly, I can define as E2t plus E2 star t. This is again real of E2t. Now, E1t and E2t, they should be somehow related to the main field E1, main field E that is coming from the source point S. So, I can write E1, which is a function of t, is some fraction beta, this is a multiplicity factor, beta 1 of the field that was there at S at some time t minus big T1, because two waves are coming at two different paths. So, I want to find out what is t, and that t should be related to the electric field at the point S sometime before T1. So, that is why t minus T1. In a similar way, E2 that is reaching at the point related to the field at the point should be some B2 E, then T minus T2. Note it, you should note the picture here that two fields are coming in two different paths. So, this is one field that is coming to this path, and this is another field that is coming into this path, and this is P, and in the P, these two E1P and E2P, that is from the source S1 and S2 coming from the source S, and these two paths are different. This is path 1 and path 2, and that is why what happened, that if when I defined the electric field at point P, this should be some fraction of the source field multiplied by the source field at some earlier time T1 and T2 respectively. So, this beta 1, beta 2, as I mentioned, take accounts the change of the amplitude because it is moving some path, and this T j I write at a stretch, j can be taking the value 1 and 2. This is a technical, this has a technical name, and this is called the time of flight. for the light field propagating along. The path J. Okay. Now, if I want to find out what is the irradiance at the point P, the total irradiance, the total intensity or irradiance at point P is IP. If I define it as IP, then IP is, as per our notation, epsilon 0 C multiplied by the time average of the field that is there, and that field is E superposition of E1 and E2. So, E1P plus E2P square of that over time average. So, that is the total intensity one can have at this point E based on the structure, whatever the structure is shown here, very straightforward and simple structure. So, these I can expand like epsilon naught C, and this is the time average of E1P square of that plus time average of E2P square of this time average plus 2 of E1P and E2P time average. So, that is the interesting term, because that is basically the interference term that one can have there. So, I can write now IP as IP as I1P plus I2P plus half of epsilon naught C and then E1. So, if I go back, what was that term? Let us see. That was E1P multiplied by E2P. Now, I should write that E1P is E1 plus E1 star and E2P was E2 multiplied into plus E2 star. So, when I have E1P, so let me write it here, E1P, E2P, this is essentially 1 by 4, then E1 plus E1 star multiplied by E2 plus E2 star. Okay, that multiplication I am writing here in this page. Okay, I need to erase this. Okay, so if I do, then one term I will have E1, E2, then one term I have E1 star E2, then we have one term E1 star E2 and E1 E2 star. Okay, where this quantity is simply epsilon naught C E IP square. This term is epsilon naught C E 2p square, and rest of the term is just the expansion of the quantity E1p and then E2p. This is the expansion by writing in terms of E1 and E2. So after having that, when we have, so this is the, as I mentioned, this is the important interference term. This is the interference term. Now it is easy to show that E1, E2, this average is time average should be 0, and E1 star, E2 star, this time average is 0. So this term involves time average of sine and cosine factor, and that oscillates at 2 omega frequency. So that's why this term will vanish. This is simply the term that will contain sine or cosine that will vibrate at the frequency 2 omega. That's why this is 0. On the other hand, other two terms with star not star and star not star will be still there. So if I rewrite this IP, then IP will be I1p, that is the intensity at point P is due to the intensity due at P due to source 1, intensity at P due to source 2, and I have some interesting interference term because of the field at source 1 and source 2, which I can write as E1 E2, E1 star E2 and E1 E2 star. This will be a lengthy calculation, so I'm not going to, it seems I'm not going to cover this in single class, but let me proceed with few more lines and then maybe I can stop. So this I can simplify, right? IP 2 plus half of epsilon naught C, and then this is 2 of, I can write as real of the time average of any one. So E1 say E2 star. Now mind it, we had the form of E1 and E2. So let me write it once again. This was beta 1, then E t minus T1, and this was 2 beta 2 E t minus T2, where T1 and T2 are time of flight. So if I introduce these two terms, T1 and T2, here in plugging these interference term, then let's see what we get. Then I can get the intensity at point P is due to the intensity of point 1 plus intensity due to point 2, and then I have epsilon naught C and then beta 1, beta 2, that is amplitude part, nothing to do is time average, so I can take it out, and then we have real part of this quantity, which is E t minus t1. So now I enter into the source field. Now the expression is written in terms of source field t minus t2. So E t minus t1 and E t minus t2 star actually can be written now in the form that we had in the earlier during the definition, the first definition. The first definition, if you remember, I wrote it Et equal to E0 e to the power I omega t e to the power I phi t. So that means when I write it in that particular form, then it should be equal to E0 square e to the power of I minus omega, then I write t minus t1 and e to the power of I phi t minus t1. This is for 1, and for other case it will be e to the power of I omega t minus t2 and e to the power of minus I phi t minus t2. So I just replace whatever the form. So the form that we had, let me write it, Et, that was the form. I considered this as E naught e to the power of minus I omega t e to the power of I phi t. That was the original form, explicit form we consider, and I put it. So today I don't have much time to proceed the calculation, so that's why I need to stop here. So in the next class again we will start from this particular point, and then we extend our calculation and show that how this interference term essentially leads to something called the coherence, and degree of coherence can be calculated from this interference term itself. So with that note, I like to conclude here. See you in the next class. Thank you for your attention.